This lecture, we're going to look at resonance structures in more detail before going back to the chemistry of the allyl functional group. So what we're talking about again is resonance structures. Now, what resonance structures allow us to do is they allow us to more accurately represent molecules. If you think about what we've done so far, we've used bond line structures to get really far in organic chemistry. So let's ask the question, if so far we've used bond line structures, let's reflect on the things that they do well. They describe nuclear position very well. They suggest when pi bonds are present. And by that, I mean we have like double bonds and triple bonds. And they describe sigma bond networks. But one thing that we actually have known for a while is they don't really do a good job of super precisely showing where electrons actually exist or how they are distributed. So, but bond line structures don't precisely show how electrons are distributed in a molecule. Okay, so what I mean by that is if we say that A and B have a double bond, that's helpful because it tells us that we have one sigma and one pi bond. This gets the gold star. That's super helpful. But it suggests that 4 electrons are equally shared between the 2 atoms. And what I would recommend us to remember is that we've known for a long time that's not the case. Like, for example, in electronegative atoms, we would show that they are polarized by having little symbols for deltas. We even had distorted molecular orbitals to show kind of this distorted like oval where there's a big lobe over the electronegative atom and a tiny lobe over the electropositive atom. We know they're not shared equally. So that's related to how they're distributed within the molecule. So what we do is we use resonance structures and other things like dipoles and that sort of thing to indicate how the electrons are more accurately distributed, or in reality, how they're distributed between 2 atoms. So in addition to depictions of dipoles, I don't know why that's red. Shoot, I'm sorry, that's going to bother me. I mean, I know why it's red. It's because I didn't delete it. Change the ink color. In addition to depictions of dipole moments, we can use resonance structures to show how electrons are distributed. Okay, now what resonance structures allow us to do is they allow us to take a system like this and actually push the electrons over to one side. For example, if the electrons, instead of being in the pi system, were equally shared between the two, the A and B, we push them over to the B and we say they're localized on the B. Then we would say B is probably negatively charged in this instance for this resonance structure, and then A is positively charged. The charges still balance out. We could just as easily push the electrons over to A to have a negative charge on A and a positive charge on B. And all of these are shown in brackets to represent that we have resonance structures describing a single molecule. Now we can actually use curly arrows to do this. If we call like this pathway A and B respectively, then I would say we could use a curly arrow. Gosh, I've got that backwards. We could use a curly arrow to push the electrons onto B, and that would be lead us through path B. Now, similarly, we could have the arrow going in the opposite direction for A. That would lead us to pathway A, where A has the lone pair of electrons and the negative charge. So we can move the electrons in either side. That's one example of a classic resonance structure. So an easy resonance structure that we used quite a bit in the alkene section of the class is to take some alkene and push the electrons to one side or the other. Now, it turns out that if we have substitution, it might make more sense to push the electrons over to the less substituted carbon, leaving a positive charge in the more substituted carbon. So this was an example of a resonance structure. I would say it's easy just because it's kind of a nice starter resonance structure. Like if you have a double bond, you can draw a resonance structure where you push the electrons over to one side and get a plus and a minus at the respective elements. So what I want to do in this lecture is talk about rules for drawing resonance structures so that we could get into things that are more advanced. So a really nice advanced one would be one where we actually take advantage of lone pairs. So here's a classic one where we have a lone pair on this nitrogen atom. And we push the electrons from the lone pair over to make a nitrogen-carbon double bond, push the electrons from the carbon-oxygen double bond up to make a negative charge, and we get something like this. This is a very important resonance structure for understanding some important biomolecules. Okay, so we need to get to the point where we're able to draw the more advanced resonance structure. So how do we do that? Well, there's a bunch of ways to do that. Let's go ahead and kind of go through some rules. So, rules for drawing resonance structures. Are number one, no breaking sigma bonds. Number two, no changing nuclear position. Okay, so there's a couple of no's right off the bat. So no breaking sigma bonds, this means don't break single bonds because all single bonds are sigma bonds. And then no changing nuclear position, this means don't move atoms. So what can you do? Well, if you're not moving atoms, this is sort of what can you do is related to what can you move. You can move electrons. Excuse me. And related to number one, as long as they don't form sigma bonds. That is, as long as they're not part of single bonds, you can move them, which allows us to move things like the electrons in pi bonds. Pi bonds are our double and triple bonds. Okay. You can move electrons in pi bonds, but you can also move electrons in electrons that are lone pairs. Okay. What else sort of gets moved? Well, I'm going to put a kind of in front of this one. Charges can move, but they really move in response to where the electrons are going. So it's not really correct to say that charges are moving. What we're doing is we're moving the electrons, and then we calculate the formal charge afterwards to see what the charges become. Let's look at an example of this. We've talked a lot about the allyl cation. What I can do with the allyl cation is, first of all, draw it. So that's thinking about the carbon next to an alkene. It's got a positive charge. That's an allyl cation. What I'm going to do is I'm going to take these pi electrons and just flip them over, move them over so that they're between the carbon-carbon, between the middle carbon and the carbon to the right. When I do that, I actually now have a neutral element on the right, and I'm positively charged on the left. That's because the left carbon once had a double bond, now it doesn't. It's lost electrons. And if you look at its formal charge, it's now +1, whereas the carbon that's on the right that was positively charged has received the electrons. I know these structures look the same, but since we can't move nuclear position or move atoms, these are in fact different resonance structures. And recall, more resonance structures equals more stability. So it's important to consider both of these. Okay, so charges kind of move. Now, another very important example is our alkene. I'll keep going back to this, where we spin the electrons over to one side, usually the less substituted side. You could say we've moved charges because we've moved two neutrally charged atoms to becoming plus and minus. But again, what's happened is we've moved the electrons, and now we react to the formal charge as a result of just redistributing the electrons. We pick up a lone pair of electrons on this right-handed carbon, giving it a -1 charge, and the plus charge emerges in the center. Overall, we're still neutral. The overall charge is always balanced. So if we start positive, as in the case of the allyl cation, we end positive. If we start neutral, we end neutral. It might mean that there's some charges we have to kind of cancel out, but we're still neutral overall. Okay, so the last thing we want to consider is another don't. So don't ever exceed the octet rule. Now notice I didn't say break the octet rule. I said don't exceed, meaning have more than 8 electrons. Okay, don't ever have more than 8 electrons. So we don't want to exceed the octet rule. And this is really when using our second row elements, carbon, nitrogen, and oxygen. But these are the elements we use, right? I mean, we use carbon, nitrogen, oxygen, hydrogen, sure. Okay, we just don't, so because we use these, I've just laid down a pretty blanket statement. Let's not exceed the octet rule ever when using these elements. Sure, if we use sulfur, phosphorus, whatever, we can exceed the octet rule a little bit then, but we're not going to look too much into that in this class. Okay. So what that means is if we consider this structure here, I'm going to show 3 lone pairs on the oxygen so you can see why it has a -1 formal charge. Okay, a good resonance structure, but an advanced resonance structure would be where we move this carbon-oxygen double bond over and then push this carbon-oxygen double bond up to put a negative charge up at the top oxygen. I guess I'll just draw the lone pairs so that we keep track of everything. So we convert a lone pair on the lower right into a carbon-oxygen double bond. And don't worry if you're not following these yet, this is kind of the purpose of the class, but I just want to show a good one versus a bad one. Okay, So this is a good resonance structure because we've moved lone pairs over to make a new pi bond. Then we broke a pi bond to make a new lone pair. Lone pair to pi bond transitions, perfect. Okay, but what if we instead went over this way? We would have a positive charge here. And excuse me, this oxygen would still be negatively charged. We'd have a double bond here. Well, the problem with the double bond there is if we do that, we've added electrons to a carbon that already had an octet. That carbon already had 4 bonds to it. So we have to say no, broke the octet. So this is not a resonance structure going to the left. The one going to the right looks just fine, but going to the left doesn't work because we break the octet rule. Here's another example. Let's say we've got a central atom with a lone pair, 2 lone pairs, an oxygen, and we have a CH3 on the left and a CH2 with a positive charge on the right. We could push the electrons from the lone pair down to make a double bond. That's a terrific resonance structure because we then neutralize the carbon having a positive charge. The oxygen now has a positive charge, but actually in this case, every element has an octet. This is a terrific resonance structure. But if we took those lone pairs and went to the other side, now I'm going to be consistent. Doesn't matter which lone pair you pick, okay? So if we take either lone pair and go to the other side, now we put electrons on a carbon that already had an octet. That's going to break the octet rule by exceeding 8 electrons to make for a bad resonance structure. Okay, so we've broken the octet rule in each of these cases. Now, what we're going to look at next time is we're going to actually figure out if we can rank the resonance structures in order of being the best resonance structure. I've kind of hinted that some resonance structures are better than others. Now, there's clear ones that violate rules. Maybe I'll show another one. What if we let's say we've got something like this, and I'm like, okay, let's add another carbon. Okay, so I've got 6 carbons total, a plus charge, second to the right. Okay, let's say I do this. I'm going to move this over here. Now, if I move that over there, then I've got a, this atom. I kind of picked a tough example. Okay, those atoms match. And what I did was I broke the bond that connected, whoops, we don't need a highlighter for that. I broke the bond that connected these 2 carbons together by moving the electrons over to make a double bond. Now I neutralize that carbon on the right, and I guess I leave behind a positive charge over here, but I can't do that. I can't do that because this takes electrons and moves them, and these electrons were from a sigma bond. And if we do that, breaking sigma bonds, that's a reaction, right? Because if you look now, we've actually separated these molecules. They can actually fall away from each other. They're no longer bonded. So you can't break sigma bonds. That's one of the early rules that we had talked about. The other one is changing nuclear position. You can't roll things around. So even if you, let's say I go back to this, I kind of draw this over here. This is a negative, this is a positive, that looks good. But if I had drawn this as R negative and positive, I actually can't do that because I can't move atoms. So just by even rolling the molecule around, I'm actually violating the rules of resonance structures, because resonance structures say, hey, let's fix all the atoms in place and see if we can redistribute the electrons in different bond line structures to get a better idea of what's actually happening with the molecule. Okay, so I'm going to end here. Next time, we're going to be talking about the rules, what makes for a really good resonance structure. Okay, so I'll see you next time.